Black hole candidate. A black hole candidate is an object that appears to behave like a black hole, but scientists have not yet gathered enough evidence to confirm it completely. Most are discovered when nearby gas or stars move in strange ways, revealing the presence of an invisible object with enormous gravity. As telescopes improve and more observations become available, many black hole candidates are eventually confirmed. They are important because they often become the starting point for discovering entirely new black holes across the universe. Stellar black hole. A stellar black hole forms when a very massive star reaches the end of its life. After burning through its nuclear fuel, the star can no longer support itself against gravity. It explodes as a supernova, and if the remaining core is heavy enough, it collapses into an incredibly small region where gravity becomes so strong that not even light can escape. These are the most common black holes known today. They usually contain between about 5 and 100 times the mass of the Sun and are scattered throughout galaxies, including our own Milky Way. Intermediate mass black hole. An intermediate mass black hole fills the gap between stellar black holes and the enormous black holes found in galaxy centers. They are thought to contain hundreds to hundreds of thousands of solar masses. For many years, astronomers searched for them because they seemed to be missing from observations. Today, evidence suggests they exist inside some dense star clusters and small galaxies. They may have formed through repeated collisions and mergers of stars or smaller black holes, making them an important clue to understanding how larger black holes grow over time. Supermassive black hole. A supermassive black hole is the largest common type of black hole known. It can contain millions or even billions of times the Sun's mass. Almost every large galaxy appears to have one at its center. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, and its gravity helps shape the movement of stars near the galactic core. Scientists are still studying how these giants formed so early in the universe, but they are believed to grow by absorbing gas, dust, stars, and by merging with other black holes during galaxy collisions. Ultramassive black hole. An ultramassive black hole is an extreme version of a supermassive black hole. These giants can exceed 10 billion times the mass of the Sun. They are found in some of the largest known galaxies and have grown over billions of years through continuous feeding and repeated mergers. Their gravity influences entire galaxies and even affects the movement of surrounding galaxy clusters. Because they represent the upper limit of black hole growth, they challenge many existing ideas about how black holes evolve. Primordial black hole. A primordial black hole is a hypothetical type of black hole that may have formed shortly after the Big Bang. Unlike other black holes, it would not come from a collapsing star. Instead, it could have been created by extremely dense regions in the early universe where matter was unevenly distributed. Depending on how they formed, they might range from microscopic sizes to many times the mass of the Sun. Although none have been confirmed, scientists continue searching for them because they could help explain some of the mysterious dark matter in the universe. Micro-black hole. A micro-black hole is a theoretical black hole with an extremely small mass and size. Some ideas in modern physics suggest that tiny black holes might briefly appear during very high-energy particle collisions, or under conditions that existed in the early universe. If they do exist, they would lose energy through Hawking radiation and disappear almost instantly. No micro-black hole has ever been detected, but the concept helps physicists explore the relationship between gravity and quantum mechanics. Schwarzschild black hole. A Schwarzschild black hole is the simplest mathematical model of a black hole. It has mass but no electric charge and no rotation. Its shape is perfectly spherical, making it much easier to study than more realistic black holes. Although actual black holes almost always rotate, The Schwarzschild model remains one of the foundations of modern astrophysics because it provides the first exact solution to Einstein's equations describing a black hole. Kerr black hole. A Kerr black hole is a rotating black hole and is considered the most realistic model for black holes found in nature. As it spins, it drags the very fabric of space and time around itself, a phenomenon known as frame dragging. This creates a special region outside the event horizon called the ergosphere, where objects cannot remain still. Rotation also changes the shape of the black hole, making it slightly flattened instead of perfectly spherical. Most observed black holes are expected to belong to this category because stars naturally rotate before collapsing. Reissner Nordström black hole. A Reissner Nordström black hole is a theoretical black hole that has electric charge but does not rotate. In reality, astronomers do not expect black holes to keep large electric charges because they would quickly attract opposite charges from their surroundings and become nearly neutral. Even so, this model plays an important role in theoretical physics by helping scientists understand how electric forces interact with extreme gravity. Kerr-Newman black hole. A Kerr-Newman black hole is the most complete mathematical description of a classical black hole. It has mass, rotation, and electric charge all at the same time. While such black holes are unlikely to exist naturally with a significant charge, they provide an important framework for testing Einstein's theory of general relativity and exploring the behavior of space and time under the most extreme conditions imaginable. Evaporating black hole. An evaporating black hole is a black hole that gradually loses mass through a theoretical process called Hawking radiation. According to this idea, quantum effects near the event horizon allow tiny amounts of energy to escape into space. Over an incredibly long time, the black hole slowly shrinks. For large black holes, this process takes far longer than the current age of the universe. But tiny black holes, if they exist, would disappear much more quickly. The idea of black hole evaporation has become one of the most important connections between quantum physics and gravity.